Hello everyone, here's the paper we are going to present today. It is called ADAM. It's a method for stochastic optimization. ADAM stands for Adaptive Moment Estimation, and it is a popular algorithm used in training deep neural networks. And it is all about adapting the learning rate based on the gradient history, making it efficient for optimizing complex models. And by adjusting the learning rate dynamically, ADAM helps neural networks converge faster during training. First of all, before moving into the ADAM algorithm, we need to know what is exponentially weighted moving average. It is a theory behind ADAM, which is commonly used for smoothing time series data. This helps reducing the noise or fluctuations in gradient estimates, providing a smoother estimate of the gradient direction. Here is the formula represents the EWMA. It is mt equals to beta mt minus 1 plus 1 minus beta times theta t. So mt represents the moving average at time t, and beta is the smoothing factor that controls the rate of decay for all the observations. So 1 minus beta is the weight given to the previous moving average, and theta t is the data point at time t. So this is the recursive function used to compute the EWMA with the weight assigned to previous moving average and current data point. So the process will be continuing until reach the base term m0, at which point we could obtain beta power of k times 1 minus beta. Beta ranges between 0 and 1. So based on the formula beta k times 1 minus beta, the weight becomes smaller as k becomes larger. In other words, as we go back further in history, the weight becomes smaller. The smaller weights will be assigned to older observations. So the weight falls exponentially as the data points get older, hence the name exponentially weighted. However, when using the EWMA to compute the moments of gradients, there can be initializations of bias, especially during the initial time steps. This bias can lead to inaccurate moment estimates, particularly when the decay rates are close to 1. So to counteract this bias, the bias correction is applied to adjust the initial estimates of the moving average. This helps improve the accuracy of the estimates over the time, leading to better performance of the optimization algorithm. The next thing we need to know is gradient descent with momentum. It enhances the traditional gradient descent by incorporating momentum. It accelerates the optimization process. In other words, we just want the learning to be slowed down vertically but speed up horizontally. It computes the moving average of past gradients, allowing it to address issues like oscillations and slow convergence of encounter with vanilla gradient descent. Here is the formula for calculating the gradient descent with momentum. GT represents the gradient descent, and the next thing we need to update the MT using the EWMA function given before. And the last thing we need to update theta t. So on iteration t, firstly we need to compute the gradients for both weight and bias on current mini batch. The next thing we need to compute the second momentum vector for both gradients of bias and weights at time step t. The last step is we need to update the weight w and bias b. Before moving into ADAM algorithm, the last thing we need to know is root mean square prob. It is an optimization algorithm that addresses the limitation of traditional gradient descent by incorporating a weighted moving average of square gradients, which effectively represents the variance of gradients. During each iteration, the RMS prob will compute the gradients for the current mini batch and updates the moving average for both gradients and square gradients. So the update formulas for this moving average are S equals to beta S plus 1 minus beta times the gradients of the weights and biases, respectively. So the weight and bias parameters are then updated using the computed moving average. Additionally, in RMS prob, the learning rate in the weight update is divided by the square root of the moving average of square gradients. This adjustment of the learning rate ensures that When the variance of gradient is high, the learning rate is reduced to take more conservative steps. Conversely, when the variance of gradients is low, the learning rate is increased, allowing for faster convergence towards the optimum. This adaptive adjustment of the learning rate helps the RMS probe to navigate the optimization landscape and converge efficiently. Here is the ADAM algorithm. What is the requirement of ADAM algorithm? It is alpha, known as step size. And the next thing is beta. It is exponential decay rate, known as the smoothing factor. And the next thing is f of theta. It is stochastic objective function with parameters theta. The next thing is the theta O. It is initial parameter vector. The first thing we need to do is the initialization of first moment vector and second moment vector, and the time step. We initialize these values to 0. For each iteration t, the ADAM will compute the gradient gt. It is the derivative of the objective function which we are trying to minimize. Therefore, it represents the direction in which the function increases most rapidly. Then we need to update the first moment vector m. It stores the moving average of the gradients, and it is the combination of the previous value of m and the new gradient, weighted by parameters beta 1 and 1 minus beta 1 respectively. And similarly, we need to update the b, and it is the second moment vector, and it gives an estimate of the variance of the gradients, and it stores the square gradients that are accumulated. Just same as the first moment, this is also a weighted combination, but of a past square gradients and the current square gradients. The next thing we need to do is bias correction. Since m and v are initialized to 0, they are biased to a 0, which leads to a bias towards 0, especially during the initial time steps. ADAM overcomes this bias by correcting the vector by the decay rate, which is beta 1 for m and beta 2 for v. So this correction is important as it ensures that the moving average are more representative, particularly in the early stages of training. The final step is the update of the model parameters. This step is where the actual optimization takes place. Moving the parameters in the direction that minimizes the loss function, the update utilizes the adaptive learning rate calculated in the previous step. And the epsilon here is added to prevent the division by 0 and maintain the numerical stability.
I'm going to compare different optimization algorithms and discuss how they are developed. So the first algorithm is a stochastic gradient descent. It simply updates the parameters using a fixed learning rate and a gradient from a current position. So it doesn't have much flexibility. One improvement was using momentum. So the idea of a momentum is when we update the parameters, not only we consider the gradient from current position, but also history gradient. So it will potentially update the parameters faster and reduce the number of iterations. Another improvement for SGDM is consider not only consider the historical gradient but also next gradient, and that's NAG. Because if we're facing a critical point in front of us, we want to slow our movement and rather than go over that critical point. But these two algorithms still have a fixed learning rate. So later on, other algorithms were developed to have a adaptive learning rate. So one is adaptive gradient. So this algorithm updates the parameters differently using different learning rate. So the idea is to keep track of all the gradient from previous steps, and if one parameter's gradient changes a lot, then the learning rate will be smaller, and if it doesn't change a lot, then the parameter will update faster. But because it uses all the gradient from previous steps, so if a model iterates too much, then the learning rate will get too small, near zero. The roots mean square propagation improved this idea by using exponential weighted average. So the model will focusing on the gradient near to the current position and forgets the gradients from far away. The ADAM algorithm uses both of this idea to improve the performance. So the first MT is momentum, and the second line is updating the learning rate adaptively. ADAM also uses bias correction. There are many advantages of using ADAM. So it is straightforward to implement, computationally efficient, and it uses a little memory, and it is invariant to diagonal rescaling of a gradient, and it is well suited for problems that have large data or large parameters. It is appropriate for non-stationary objectives, and it also be easier to work with hyperparameters. But it also have some limitations. First is it might not always convergent, and the second one is it has potentially will have an over-fitting problem. Here are some results that author did for comparison from ADAM to other algorithms, and from those figures we can see that ADAM has a lower training cost among the lowest training cost among all the algorithms on all of the models, including logistic regression and some neural networks.